So later on, we will spend more time on these kinds of functions. So functions of the form e to the x or a to the x, log functions, so some log to some base a of x, and then this is x to the n. They are not the same. In fact, we can even change this base to any other base, and these functions are not the same. But now we'll consider special cases of these functions and then the kind of operations that we can perform on them. So an expression like this is an exponential. So this value a, this is your base, and this value here is the exponent or the power or the index. The thing about the base is that it's a positive number and it's usually not 0 or 1, because if a is 0, then a to the n is 0 for n not being 0. But then you get these kind of weird things like 0 to the power 0. The question is, what is this? Can it be 1? Because I know you've been told that any number to the power 0 equals 1. Well, this obviously does not make sense if the number is 0. It doesn't make sense. So we don't discuss the cases where a is 0. And if a is 1, you've got 1 to all powers. So 1 to any power is just 1. So that's not interesting. So we will require positive real numbers. Now, the important thing about positive real numbers is that we're saying that the base a is greater than 0, which means there were two possible cases. You could have the base being a fraction between a and 1, or you could have the base being bigger than 1. And what happens to the exponential depends on the value of the base. So we'll come to that as time goes on. For now, we'll let our indexes be integers. So in other words, we are considering a to the power n. So I'm considering a to the power n, where a is greater than 0, a not being equal to 1, and n being an integer. And this is the classic definition of indices. So we'll take a few examples. If you have 5, as we say, the base here is 5. The index here is 3. It gives me 5 times 5 times 5. That's 125. And then with the base, if the base is 3 and the index is 4, you have 3, 3, 3, 3. If you multiply that, you get 81. Now, exponentials are different from powers like this. So notice that in the case of the exponential, the base is constant and the index is changing. In the second case, the base is changing and the index is constant. So x squared is not the same as 2 to the power x. In fact, if you sketch these two, you will notice that 2 to the power x grows much faster than x squared, much, much, much faster. If you draw a graph, so let's do it again, you will see that your x squared looks a bit like this. 2 to the power x begins to grow much, much faster. And exponential growth is important. It is the mathematics that underlines compound interest. So it's important to understand how it works. Now, the indices obey certain laws, and I've listed a few of them here. So we're taking our bases not to be 0 or 1. So they are positive real numbers, and we're taking the m and the n are going to be our indexes. Then the following are true. The first one says that if you have a raised to the power m times a raised to the power n, where the base is the same, it equals a raised to the power m plus n. The second case, you have a raised to the power m divided by a raised to the power n, is obtained by subtracting the index n from the index m. You can also chain indexes here. a to the power m to the power n is a to the power m times n. The fourth one is a to the power 0 is 1. And the fifth one is key. Or this is not even the fifth one, but this one tells me that if the bases are the same in this equation, their indexes are the same. And it's an if and only if. So in both directions. So we'll make this 5. We talked about negative exponents being expressed as fractions. 6, we talked about the fact that you can split up the base if it is a product. So for instance, 6 to the power 3 is the same as 2 to the power 3 times 3 to the power 3. And then 7, the same thing happens, but now you're writing the index as the quotient. And then the 8th one is any number raised to the power 1 is the number itself. Keeping in mind that we're just discussing this for our basis. Now, what do we need these for? Well, we need this to simplify expressions. And then we also need them to solve exponential and in later on log equations. So we'll see why this is important. Now, we can also consider fractional indexes, and later on we will discuss what we call radicals as well to follow. So given a base A, we can talk about A raised to the power 1 over n to be the nth root of A. Now, the reason we talk about the nth root of A is because if A raised to the power 1 over n equals B, it means that B to the n is A. For instance, like as we have here, you have 27 to the power 1 over 3 is the cube root of 27. That's 3 because 3 cubed is 27. And we can actually use the laws of indices to work this out. And again, 64 to the 1/6 is 2. Now, you will notice that negative 2 is also a solution. So that's why I didn't qualify this as an if and only if, because they are possible, they're different. Sometimes there are different solutions. And then for the square root here, 49, you get 7, but obviously minus 7 is also a solution. So when we want to talk about the root functions, if it's an odd root, so cube root, fifth root, and so on, you know there's only one number. But if it's an even root, you could have a positive or a negative. So we will come to this and we'll discuss simplifying these expressions in class so that we will see how to simplify these. And we will use all of the rules that have been discussed here and here to discuss them. So try them on your own. We'll discuss that in the classroom. The same way, we can use the laws of indices to solve these. Now remember, we said that a to the m equals a to the n if and only if m and n are the same. So now we've got this equation, 3 to the x equals 81. This 3 and this 81 are not the same, but I can write 81 as 3 to the power 4. So it reduces to 3 to the x equals 3 to the 4. So my x is 4. And once you know how to do this one, 2 and 3 should be straightforward. 4 is quite interesting because this now is not that kind where you can have this sort of equation, but it turns out to form a quadratic equation in y, where y is 3 to the x. And so what you do is that it's a two-step process. So the step 1 or maybe 3-step process, you obtain the quadratic equation. 2, you solve it. And then 3, solve the resulting exponential equations. So we'll discuss that in the classroom. Now, indices and logarithms are cousins. In fact, they are two sides of the same coin. So when we get to logs, we will now see that logarithms are indexes. In fact, they are exponents. And so the definition of the logarithm of a function actually returns exponents. So in the next video, we will talk about what logs are and how to work with them.